Hi everyone, welcome. Let's begin. So I'm delighted to welcome fellows and visitors to what is the fifth discussion meeting of the 2024 session. We'll be discussing the paper Methods for Estimating the Exposure Response Curve to Inform the New Safety Standards for Fine Particulate Matter by Michael Cork and co-authors. Mork and Dominici from Harvard University in the USA. So we're running this as a hybrid meeting. We have lots of people who've joined online as well. So the meeting, we're here at Imperial College London for the Royal Statistical Society, but we welcome an online audience. Please do keep your microphones muted if you are online and cameras turned off, unless called to speak during the open session later. A recording of the meeting will be posted on the RSS YouTube channel. If anyone prefers not to be filmed, let us know and we can edit that part out. If you experience any technical problems, please use the online chat box. We have Judith here from the RSS to help in our support team to help you. So a big part of these meetings is to have a discussion after the presentation. So we actively encourage everyone to contribute to this discussion of the paper in the open session that follows the main presentation, which lasts about 30 minutes. So actually we have a lot of time for discussion. We have some invited discussants, but then there will be an open session. So anyone can speak and just give your name and affiliation, please. And your comments can be brief or up to 5 minutes. So there's no lower bound. There is an upper bound of 5 minutes, but no lower bound. So it can be brief. It doesn't have to be 5 minutes, but not longer. And similarly for the journal, you can also write up your discussion as a sort of mini publication in the journal later, again, an upper bound of 400 words, and that will be published in the journal along with the paper. So it's kind of a nice mini publication if you work in this research area and would like to comment on the paper or how your own research links with the paper, then we welcome such contributions and the authors will reply to any questions raised in those discussions, and that is also published in the journal. So this is kind of a history of the society that goes back almost 200 years, and we keep going today to have these discussion meetings. So we'll begin with the presentation. So the paper will be presented by Michael Cork, visiting from Harvard University. The paper will be published in Series A of the Journal of the Royal Statistical Society. And yeah, over to you, Michael. Thank you. Thank you for coming.
Yes. Just want to start by saying thank you all for being here. Thank you, Adam and Judith, for making this happen. It's really cool to be able to be here and present in person. So I'm going to start by just introducing some of the main topics that I explore in this paper. And this is joint work with my advisor, Dr. Francesca Dominici at Harvard, and a mentor, Dr. Daniel Mork. So I want to first motivate why it's important to think about an exposure response curve generally for air pollution. The reason is air pollution is actually the leading environmental risk factor for early death. It contributes to more deaths worldwide than traffic collisions. You know, I think as researchers in this field, we're aware of this, but it's interesting as the general public, I think we've done a good job of explaining to them that polluting our waters or our food is really detrimental, but I think our air or more of our built environment, there's more work to be done. This is motivated in the context of the US, and this is true in a lot of places, but in the US, there's 40% of Americans live with unhealthy PM 2.5 levels. And unhealthy here is actually a pretty large number. It's 35 micrograms per meter cubed. If that number means nothing to you, it'll mean something a little bit later. But so this is a big problem facing a lot of people. And fine particulate matter, which I'm calling PM 2.5, here the 2.5 refers to the actual diameter of the pollution. It's a really small pollutant. It contributes to a variety of adverse health outcomes that we know of, some of which are listed here. We have COPD, diabetes, a lot of different adverse health outcomes are affected. So why are exposure response curves important? And by exposure response curve, I mean the relationship and the causal relationship between a continuous exposure and a response, for example, hospitalizations, mortality. And it's because they're really important for setting policy limits. For example, the WHO produces global air guidelines. Recently, they were set from 10 micrograms to 5, mostly informed by evidence from these exposure response curves. In the US, the EPA sets these national ambient air quality standard, the NAAQS, and in their mandate, it requires them to ensure a margin of safety, but that is a little bit of ambiguous language. So it requires evidence from things like exposure response curves. So here's an example, right? These are 3 different plausible exposure response curves that could be the case for air pollution. We have a threshold, which is in blue, which is seen in a lot of different toxicology studies where we might have a certain value of the exposure where if it's low enough, there's actually no effect. And then after a certain value, it starts having a detrimental effect. You could have on the opposite end, something like a sublinear relationship shown in green, where pretty immediately you start seeing a pretty marked effect on an outcome, for example, health or hospitalizations. Or you might have a linear relationship with someone in the middle, right? And if you have these different plausible ERCs, they would all, I think, inform policymakers differently, right? If you have a threshold, you might set a limit near that threshold. Whereas if you have a sublinear, you might even set a stricter limit. I think it's important to remember that in all of these cases, right, you're trying to argue for a strict limit, whereas industry and other people would like the limit to be as large as possible. So again, we have to have pretty marked evidence to be able to inform governmental bodies. Okay, so if these are really important, and what's so hard about estimating them? So one of the hardest parts is that to establish a causal link between any continuous exposure like PM and health is challenging due to the data that we have, right? We rely on observational data. There's no experimental, there's more experimental data. We can't randomize people to receive certain levels of exposure. And this causes a lot of issues. A primary one is confounding, right? Where you might have a factor that is biasing or distorting the relationship between an exposure and outcome, given that it's associated with both. You might have effect heterogeneity, where certain factors in the population actually influence the outcome. And if you're not aware of how those factors are distributed, it could influence the exposure response function. Also note that in this talk, I'm going to say exposure response curve or exposure response function kind of interchangeably. Or you might have also data that's kind of informed at different levels, right? You might not collect data on the exposure at the same level of precision as you do for the outcome data. So that being said, there's been a lot of work done in the field to try to estimate these exposure response curves, and I'm going to talk about a couple of them. And I'm going to start with some regression functions. So I'd say traditionally, the way these were fit in the literature is kind of fitting a linear model, right? Where you fit an outcome as a function of an exposure and also adding these different covariates in a linear way. And so this assumes linear association and includes these confounders also linearly. So this is what you might see in like an kind of an introductory epidemiology class. It leaves a lot to be desired. One of them is that the exposure is assumed to be a linear function, or the outcome is assumed to be a linear function of the exposure, which might not be the case. So to relax that assumption, people have developed nonlinear spline models, right, where you can have a nonlinear function of the exposure be affecting the outcome. And then you might adjust for the confounders also in a linear way. Other models have been developed in this space, like the ESCIF, the extended shape constrained health impact function. And one thing that's nice about this function, it's also able to detect thresholds, right? So if we expect there might be a threshold, if we don't have a method that is able to detect it, that kind of defeats the purpose. However, all of these methods I'm calling regression methods because they do not have an emphasis on, they're not have an emphasis on the design phase, or they're not causal inference methods. And I'm going to go in a little bit more detail what I mean by causal inference methods, but basically the EPA or WHO or others are prioritizing methods that are placed in this causal framework because it has some advantages in terms of trying to assess causality. So for those who are not familiar with causal inference, I'm going to give a very brief overview of it. So a lot of causal inference is in this potential outcome framework, which is kind of this counterfactual world, which is to say we're trying to impute what would have been an outcome for an individual had they received a certain level of treatment. And in causal inference frameworks, they often separate the design from the analysis stage for causal estimation. So the design stage, what you do is you actually define what your causal estimate is, and you do some sort of weighting or matching technique so that you try to emulate an experimental setup. So what we're trying to do is we have observational data, but under which assumptions and using which methods can we try to turn this observational data into the data we would have received from an experiment where we benefit from the ideas like randomization. And the way you assess how close you get to an experimental setup is you use these metrics like covariate balance. And I'll talk a little bit more about what I mean by covariate balance, because in a continuous setting, it's actually a little bit different. So the advantage of causal inference methods is under certain assumptions, there's greater robustness to model misspecification compared to traditional regression methods. I'm going to give a little bit of an overview of some of the methods that are in this space. So some of the earliest methods for causal inference for continuous exposure rely on the generalized propensity score, which is a way to model the exposure, right, as a function of covariates. And the idea is that you can use this to reweight the data such that the exposure is actually independent of your covariates. However, this is to get this correct, right, you have to actually model the propensity score correctly. And obviously that isn't known in advance. So it can be subject to model misspecification and also can generate sometimes extreme weights in the design phase, and that can make the analysis really unstable. So recently there's been some doubly robust approaches that have been developed. And here doubly robust means we're actually modeling two things. We're going to model the outcome model, what we're called nuisance functions, right? We're going to model the outcome model and the propensity score model. And it turns out if you get one of those right, that your ensuing exposure response curve will be unbiased. Then there's entropy balancing, which is instead of fitting a generalized propensity score, what it does is it creates weights such that it optimizes a covariance balance metric directly. And here what it's going to do in a continuous exposure is it's going to try to create weights such that its resulting pseudo population, the exposure is actually uncorrelated with all the covariates. The idea being that if we want to make them independent, then the correlation should be zero. But just note that if they're independent, the correlation is zero, but the opposite isn't true, right? So when we're setting the correlation to be zero, that doesn't necessarily mean they're independent. And this is actually something that will come up later in this presentation. And finally, one other way of fitting these exposure response curves is called causal GPS, which is a method developed in the past couple of years, which extends the matching framework to a continuous exposure setting. And in doing so, it does also fit a generalized propensity score using, it can use also machine learning techniques. And if you want to learn more about causal GPS, there's an entire paper and a package available for R. Okay, so each of these different methods that I've introduced address specific data concerns and causal requirements, and each has its unique strengths and weaknesses. However, we've had limited research that compares their behavior and how they fit across a variety of different plausible exposure response curves and confounding structures. So the aim of this paper was to bridge this gap and conduct a comprehensive simulation study that compares some commonly used estimators, both in the regression and causal inference buckets, for exposure response curves. Then, based on the simulation and kind of the insights from that, I'm going to fit all these different methods to estimate the relationship between long-term fine particulate matter exposure and all-cause mortality in a data set of over 68 million Medicare beneficiaries from 2000 to 2016 across the continental US. So before we get started, I want to just be clear about some of the notation I'm going to use. So what I want to do is estimate the effect of a continuous treatment E on an outcome Y, conditional on a vector of covariance C. So again, in this setting, we're using the potential outcomes framework. It's denoted like this, Y sub I of E. And what this says is what an individual I, what outcome they would have gotten had they received that level of the exposure. Again, in causal inference, right, we can think of this as a missing data problem, right? Because we only see one realization of this potential outcome, right? We only see the outcome on the exposure they actually received. Whereas what we're interested in is the potential outcome throughout the curve. So there's a lot of missing data. And so one way we stabilize these estimates a little bit is we actually focus on this causal estimand, the exposure response curve, which I'm defining in this way, which is R sub E, which is the expected value over your population of this potential outcome. So what this is saying is if everyone in this population had received this level of the exposure, what would be the mean of the outcome? The reason I focus on this is that the R sub E is policy relevant and typically well interpretable by policymakers, right? The idea of, okay, if everyone had received this level of the exposure, what would the average outcome be, is a little more interpretable. Okay, so it turns out, right, when I said for causal inference methods that under certain assumptions, they are more robust to model misspecification. I'm going to quickly go over some identifiability conditions that are needed for exposure response curve estimation. So in all causal inference settings, you have to identify some untestable or unprovable assumptions. And some common ones that are often invoked for exposure response curves are the following, right? Because you actually have observational data, and we're trying to go from observational data to a causal analysis. The first is stable unit treatment value assumption, or SUTVA, which says that each individual's outcome depends solely on their exposure. So this means that, right, my outcome is not dependent on another person's exposure value. The unconfoundedness assumption says that given a pretreatment covariate C, the potential outcomes must be independent of the received exposure. So this is saying we've measured all the potential confounders, which is a pretty strong assumption. And when we condition on them, we can get back to the potential outcomes being independent of the exposure, right? So in an experimental setup, right, we don't actually have to condition on the confounders. Randomization ensures that the potential outcomes are independent of the exposure. In an observational study, we do not, that is not the case. So we have to have this unconfoundedness assumption. And finally, the common support or positivity or overlap assumption says that the conditional density of the exposure is positive for all values within the exposure range. What this is saying is each individual, based on their covariate profile, has a non-zero probability of receiving each value of the exposure in the exposure range. So this is a pretty strong assumption. And when you have really kind of at the tails of the exposure range, this assumption might not be met. So what's often done in practice is you actually truncate the exposure, and you maybe only estimate the exposure response function from the 5th percentile to the 95th percentile, for example. And that's actually what we will do in this study. So I said we're going to compare 7 different estimators. Here they are. I'm calling the first one linear. And this is just fitting a Gaussian linear model that adjusts for the exposure in a linear way and the confounders in a linear way. GAM is a generalized additive model. So this is a spline model where we can allow a nonlinear relationship between the exposure and the outcome. And then we adjust for the covariates or confounders linearly. The change point model is something we're using as a threshold model, and you can think of it as like 2 linear models or like 2 lines with a break in them. So it allows for this kind of break point to happen. And it also linearly adjusts for the confounders. The next 3 estimators are the same in terms of the outcome model. So it's a linear model or a spline model or a change point model. But what we do is that we separate into the design phase. We do this entropy-based weights adjustment. So what we do is we take the analysis, we take the data, we fit these entropy-based weights, which reweight the data such that the exposure is uncorrelated with each of the covariates. And then we fit the outcome model. And then finally, we include GPS matching, this causal GPS, which is, again, this inference method that extends the matching procedure to the continuous exposure setting. In the paper itself, I've also included each estimator name, a description, where you can find the algorithm that fits this. And then also all of these are able to be fit pretty easily in R. And that was actually one of the requirements for this paper, is I wanted it to be something that each kind of practitioner or people in the field could feasibly fit. Okay, so I'm going to talk a little about the simulation setup. So in this simulation, I'm going to evaluate how these methods perform under a couple of different scenarios. The first being, we're actually going to change the actual relationship between the exposure and outcome. So we're going to change the marginal relationship. We're going to change the exposure model. So essentially what we're doing is we're building different ways of generating the exposure. And this is because we're actually generating different types of confounding. We're going to test for heterogeneous treatment effects. So when we include an interaction between the exposure, the confounders, and the outcome model, what we're saying is based on an individual's covariate profile, the exposure response curve is actually different. And so you can think of this as kind of similar to heterogeneous treatment effects where, right, the treatment or exposure to air pollution is actually different for each person. And then sample size, right? Sometimes we have data that's small or large. And so I'm actually going to do this across a couple of different sample sizes of 200, 1,000, and 10,000. I'm going to walk through first of how I built the simulation. So you start with confounders, right? And the confounders are generated as a mix of continuous and categorical variables. The first 4 are from a multivariate normal, where I is the identity matrix. The 5th is a discrete uniform distribution, and the 6th is a continuous uniform distribution. Then from that, we generate the exposure under 4 different scenarios. So the first, what I'm calling linear, is that the exposure is a linear function of the covariates. I had this cardinality function gamma of C, which has appeared a couple times in literature when you're evaluating exposure response curves, so I kept that. And then as a slight abuse of notation, I'm adding this normal noise, right? So I'm adding noise that is centered at what is mean 0 and a variance of 10. The heavy tail scenario, we still have a linear relationship between the covariates and the exposure, but we include a heavier tail distribution for noise. So this is from a T distribution with 3 degrees of freedom. And what this does is it basically it introduces more extreme exposure values into the data, which can sometimes be hard to handle. The third is a nonlinear case where we actually had a nonlinear relationship between one of the covariates and the exposure, and an interaction as an interaction between the two. So what I've done is I've generated the covariates. I have these 4 different exposure models. Now I want to simulate the outcome model. So the outcome model is it is simulated from a normal distribution with a standard deviation of 10 and some mean function. And so we generate the mean function from, we have three different specifications of the exposure outcome relationship, which is conveniently the same as what I showed earlier. So what we have here is you can have a threshold model, but again, where there's no effect below 5, an exposure concentration of 5. You have a sublinear, which is parameterized by this log function, or you have this linear relationship. So you have these three different plausible relationships, but you also have an interaction term. So when I include an interaction, what this means is I'm taking, for example, for the mu linear interaction, it's the same as the linear model or the linear case, except you add this interaction term, which means that the actual relationship between the exposure and the outcome varies as a function of the covariates themselves. So this means that in total, we actually have data from 72 different exposure scenarios. We have 4 exposure model specifications, 6 specifications of the mean function, 3 different sample sizes, and then in each scenario, we run 1,000 simulations. So it's 72,000 different simulations run. And actually, there's more than that because we also ran a data-informed simulation where we sample from the data set used in our application. And I'm actually not going to cover as much of that, but this is in the paper. And the reason we did that is also we want to demonstrate that, that from this simulation that it's a reasonable simulation to do and kind of validates that our approach is valid in a real world setting. Okay, so how do you evaluate estimators, right? It's a little more challenging than in a binary treatment setting, right? Because you're evaluating how well the curves approximate each other. So the way we did this is we split the exposure curve into 100 equally distanced points, and then at each point evaluate based on the bias and root mean squared error. So here, notice that I'm doing a little bit of trimming. So I have a restricted exposure range E star. Again, this is commonly done because of positivity violations. And what I'm doing here is at each value of these equally spaced points, I'm comparing the R hat of S, which is in that simulation replicate, what is the estimated exposure response function at that point minus the truth, right? Because in the simulation, unlike real life, we know what the truth is. And we're either taking the absolute bias or we're taking the root mean squared error, which is kind of more standard, this like square difference between what we estimate and the truth. So again, I talked about this a little bit, but for causal estimators, right, you have to design phase, right? So how do you know if you should proceed onto the analysis phase? Well, a common rule of thumb that's done here is if the absolute correlation in this reweighted sample is below 0.1, we say that's sufficiently close to 0 to proceed to the analysis stage, or provides enough evidence that we think these design weights are working properly. Okay, so I'm going to walk through one of the results. For the linear outcome model, and I'm going to look at the absolute bias with the sample size fixed at 1,000. So again, this is just a reminder of what we're doing, right? We have this linear relationship between the exposure and the outcome. Okay, so what I'm going to show here is at first not that interesting, but what I have on the y-axis is the absolute bias. On the x-axis is the 4 different specifications of the exposure model, which kind of specify the type of confounding that's present. And what you see is I've also included all the estimators, where the shape, what I've done is the kind of causal analog to, for example, for linear and the linear entropy weighting, it's the same shape, but it has a cross through it, so it's a little easier to follow. And the causal GPS is that star. So what I'm showing here is, in this case, which is one might think the most simple case, right, they all perform well. And in this case, right, the linear model is actually correctly specified. So we actually know by kind of standards theory that this would actually be the best estimator in this case. But I show that to compare with when we actually add some interactions in the outcome model. And this is when some interesting things start happening. So if you look farthest to the left, what you're going to see is that the regression-based estimators have substantial bias compared to before, but the causal inference methods are all able to kind of correct for that bias. However, when you get in the heavy-tailed scenario is similar. When you get to the nonlinear relationship between some of the covariates and the exposure, you see that the entropy-based adjustments are no longer kind of debiasing the results. And the same in the interaction term, whereas the causal GPS is still relatively lower bias. And I can talk a little bit more in a little bit of why this is happening. But I also wanted to show, and I apologize if this is harder to see for those who are in person, but right, we have these metrics like the absolute bias or the root mean squared error. But what we're actually doing is more close to this, right? Because we're evaluating a curve. So we're faceting on the x-axis, and now you can't see this, by the different exposure models, and the y, we're faceting by the different estimators. The dashed line is actually the truth from our simulations. The solid line is the mean from all the different 1,000 simulations. And I've included some realizations in the lighter gray to show just a little bit of the variability, although it's kind of hard to see from here. This will be in the supplementary materials. And why I wanted to show this is because I think it's important to remember that when we use a single metric to quantify a curve, we can lose some information, right? For example, the linear model in the kind of the interaction setting, right, is not getting the curve correctly at any point, whereas the GAM is kind of underestimating the curve at higher values of the exposure. But in these certain values of the absolute bias, they're actually comparable. So this is just to say that there's always some caution that should be taken when we're taking a curve and flattening it to metrics. And it can be useful to kind of plot the actual curves that you're also fitting in your simulation. So I want to take a second to give a couple of simulation insights. So first, regression methods perform well under two conditions. You correctly specify the exposure outcome relationship, right? So if you have a linear model and the actual exposure relationship is linear, it will do well, as long as there are no heterogeneous treatment effects, right? As long as there's no interaction present. So it struggles with heterogeneity, and this can cause some large bias. And something I wanted to note here is bias versus variance trade-off. So these linear models, these regression models, actually have less variance than causal inference methods. And I think the reason is because in a causal inference method, you're actually fitting two different models. You're fitting a design model and an outcome model. And so this can introduce more variance. So what's interesting is when you look at metrics like RMSE, these, even if it's a very substantially biased estimator, sometimes their RMSE can be comparable to the causal inference methods. So that's something to kind of be aware of. So for the causal inference method, some insights are that when you use entry balancing, and I'm calling first moment entry balancing when you are requiring that the exposure be uncorrelated with all the covariates. So it turns out you can actually balance higher moments as well. You can introduce and say, actually, I'm going to balance the second moment of the exposure with all the covariates. And in certain scenarios, that can actually be better. But this entry balancing performed well when heterogeneous treatment effects are present. It had reduced bias with regression models when sample size is over 200. And the GAM entry model is able to fit both a linear model or some nonlinear relationship. So some challenges is if the sample size is too small, it can be harder to fit because you have to fit this these weights, and it might not converge if you don't have enough data. So I want to add that second moment entry balancing. In the paper, we go over this a little bit more, but essentially you can reduce bias for nonlinear models if you require larger moments of the exposure to be uncorrelated with the covariates. I actually have a little bit of a slide on that later. And causal GPS was excellent with nonlinearities and interactions, but at larger sample size improved the GPS fitting and match quality. So at lower sample sizes, it turns out that causal GPS has a little bit more variance, and so I wouldn't recommend it at lower sample sizes. So based on that, I have some guidance that I kind of developed. So if you have a small simulation and no effect heterogeneity, regression methods are great, right? They actually are able to approximate this well. But for all other contexts, I recommend causal inference methods. If you have a sample size of less than 10,000, I recommend entry balancing methods with some sort of spline model. If it's larger than that, something like a causal GPS can do well. And here's this caveat about entry balancing weights is, you might ask, why not just go right to the second moment entry balancing procedure? The reason you don't want to do that is if you introduce a lot of constraints on the design model, it can create extreme weights, which increase the variability, or it might not converge. And so I kind of provide some guidance on first starting with a first moment balancing, and then you can check to see if sufficient balance is achieved by plotting the relationship between the exposure and covariates in the reweighted sample. And then if this is not flat, you can incorporate higher moments into the entry balancing procedure. This is, again, to note, if you increase moments that you are balancing against, it's going to increase the variance of your estimator. So it's not always the case you just want to uncorrelate with higher moments. Okay, so for the final part, I'm going to talk a little bit about the data application. So my study population is a Medicare cohort across the contiguous US. We have 60 million individuals and over 30,000 zip codes. We have demographics like age, sex, race, ethnicity, date of death, residential zip code. The outcome is aggregated deaths among Medicare enrollees by zip code, year, and strata. And here we define strata in the following way: by age in 5-year age bins, sex, race, ethnicity, follow-up year, and Medicaid eligibility, which is a government-funded healthcare program that is for qualified individuals by income. So this is kind of an individual level proxy for socioeconomic status. Our exposure is fine particulate matter estimates from an ensemble prediction model that we aggregate to the zip code level, kind of the same as our outcome. And then we have 10 different confounders. We have a mix of the zip code and county level variables that come from the census or from other surveys. We have meteorological variables, and we have these geographic and temporal adjustments. The outcome, we log transform all-cause mortality by zip code, year, and strata. And then we estimate the exposure response curve across from the 5th percentile to 95th percentile, again, in that truncated distribution. So just a quick note on the confounding adjustment here. So it turns out that, right, we have this confounding adjustment at the zip code year level, but our outcome is actually more specific than zip code and year because it's zip code, year, and strata. So what this means is like a little bit of a mismatch. And so one thing that's been done in the literature before is you actually do the adjustment for the confounding at the zip code year level. And then you fit the model at the zip code year strata level, and you have to reweight the model also by how much person time is observed for each zip code year strata. And we bootstrap confidence intervals using an amount of n bootstrap, and we use zip codes as a block unit in our resampling procedure, given that zip codes are correlated over time. So we want to ensure these are valid confidence intervals. So this is a plot of the covariate balance. I think it's kind of helpful to see what's happening here. So on the x-axis, you have the absolute correlation, and on the y-axis, you have these different covariates. What it's showing in red is before we do any sort of design-based metrics, that some of these exposure or these covariates are actually correlated with the exposure. And what should happen, and what we're showing is happening, is after we apply these weights, either through matching weights and causal GPS or entropy weights, that this correlation is going towards 0. So for causal GPS, you can see that these like dashed lines show the mean of the absolute correlation. And so the mean of the absolute correlation is below 0.1, again, noting that for some actual covariates themselves, it's below 0.1. And the entropy balancing is closer to 0. And you might be asking, why isn't it exactly 0, right? Because what I'm saying is when I fit entropy balancing, I'm actually requiring the absolute correlation to be 0. And the reason is we're doing a truncation procedure on these weights. So at the 99.5th percentile, we actually truncate the weights because we don't want to have extreme weights. This is kind of done to decrease the variance a little bit. So that's why they're not all exactly 0. But it's not surprising that the covariate balance is really low for entropy weighting. Okay, finally, here are the curves. The first thing you would notice is that I don't have change point models here. The reason is the change point models actually didn't converge in this data set. It's an enormous data set, over 500 million person years. And these change point models are not able to fit. And so that's actually an important consideration based on your data that you're using, is that some of these methods are not developed for this large of a data size. But some things I wanted to note about this. So on the x-axis, you have annual average PM, and the y, you have mortality rate. Notice that each of these show an increasing relationship between PM and mortality. It doesn't probably surprise anyone in this room, but it's nice to have that agreement with the literature. You also notice that in this setting, which a large sample size, we expect to affect heterogeneity. I would believe most causal GPS and gamma entropy weighting based on our simulation. And both are showing kind of evidence of maybe this sublinear relationship, or at least at low levels, there's still a pronounced effect of air pollution. Another way of showing this same plot is I'm actually fixing all of the estimators so that you're seeing the relative mortality relative to their estimated mortality at 12. Why I chose 12 micrograms per meter cubed was because this is was the actual limit for the EPA under the NACs, though it has since, at the time of me writing this article, though it has since changed to 9, but given the political climate, who knows how that will change. And what it is showing is that each of the estimators show there's a reduction in the relative mortality rate as compared to when you set it at 12. Though causal GPS, interestingly, has the most, I'd say like subtle change, or is this kind of more of a plateau, but all these show that reducing the relative mortality from 12, for example, to 9 would save a lot of lives, essentially. So some of the key insights from the data application. We have evidence for a nonlinear exposure response curve, right? Each of the, so because, and in this case, I believe most kind of gamma entropy or causal GPS estimators, because they're most plausible given our simulation study, they each show that even at low levels of the exposure, there's a marked impact on the mortality rate. So because I was unable to fit a threshold, these, what I'll call a sublinear trend, or the fact that there's an effect even at low values, seems to suggest that even if we could have fit a threshold, that a threshold model is unlikely in this setting. And the policy implication is that this kind of supports setting a more, what I call strict NAC standard, right? Which we know that even if we keep lowering the allowed annual average emissions, that this will continue to save many lives. So before I conclude, I have a couple of things to note, some of the limitations of the study. So again, this is based on simulations, and we included 72,000 different simulation replicates. However, there's also a limited set of scenarios, so there's always more scenarios we could do. We also picked 7 estimators that we selected based on availability and what we've seen done in the literature, but there are actually more estimators being done every day. There's actually a couple more that have recently been developed in the past couple of years, and I'd be happy to speak on them a little bit. And then finally, this analysis assumes this conditional independence or non-confounding assumption, which again is a strong assumption, which is saying that we assume that we've actually measured all the confounders. So in practice, we know this is really hard to achieve, but one thing that can kind of lend some confidence to the robustness of our application results is there's actually done an e-value analysis on the same data set. And the e-value, what it does is it tries to estimate how strong an unmeasured confounder would have to be to nullify your results, right? So how strong would it have to be such that actually this relationship we saw is invalid? And what it found in this case is it required a 1.32-fold risk ratio. So this would mean that it would have to have 1.32 risk ratio with the exposure and the outcome in order to nullify the observed association, which is kind of unlikely, right? I think in epidemiological analyses, usually a strong confounder is between the 1.1 and 1.2. So this helps provide a little bit of robustness, at least to the observation that, right, as we increase PM, we see mortality go up. And finally, I just want to end with saying that understanding the shape of the exposure response curve is critical for air pollution epidemiology, but not just air pollution epidemiology. There are a lot of different applications for a continuous exposure and an outcome like hospitalizations or mortality. And these findings underscore that causal inference methods are really important in shaping our pollution policies and mitigating adverse health impacts, and so kind of advocating for more causal inference methods to be used in the field. And then also, hopefully this paper can provide guidance for people who are interested in estimating these exposure response curves given their own data set in terms of sample size, confounding structure, or how they anticipate whether or not there'll be kind of heterogeneous treatment effects. And lastly, I just want to just say this funding was supported by grants to the NIH and the Alfred P. Sloan Foundation. I want to thank my collaborators who are not here today, but Dr. Francesca Dominici, who was my advisor and really helpful in this work, Dr. Daniel Mork, who's a co-author and a mentor who's contributed a lot to this work, and I'll also be grateful to the whole National Studies of Air Pollution and Health team at Harvard, who've really been helpful throughout this process. And then I also want to thank, again, Adam and Judith for helping get this event, make this event happen. Yeah, so thank you very much for listening.
So I'd now like to call on Professor Neil Pierce, London School of Hygiene and Tropical Medicine, to propose the vote of thanks.
Thanks very much, and thanks very much for the invitation to present here. I've never done one of these before, so I'm just learning what the normal format is. But it's great to be able to propose the vote of thanks. And I think we've heard a really excellent talk, which really summarizes these methods very well. And I say that to start off with because I'm going to be quite critical, but not of the actual work, which I think is really good. But I'm going to be critical of the causal inference framework in which it's been put, because as an epidemiologist, it has a number of shortcomings for me. Epidemiologists have always done causal inference, right back to the time of John Snow and others. I do causal inference all the time. I sit on committees which do this sort of thing. We review all the evidence from epidemiology, from randomized trials, from experimental animals. We review the mechanistic evidence, and we try and put it all together and come to causal conclusions. And causal inference in epidemiology has always involved putting all of the evidence together. It never relies on one single study. Even on a randomized trial, you always need to take all the other evidence into account. And that's why I think it's a real problem that the term causal inference now has become attached to a particular set of techniques. And it's a problem for two reasons. Firstly, these techniques are fantastic when used appropriately. Sometimes they're appropriate, sometimes they're not, but they're really useful. But using the label causal inference has really created a split in epidemiology between those who think that this is the only way to do causal inference, and those of us who think these are really useful methods, but they're just one set of methods that we use alongside others when we do causal inference. So for us, causal inference, as an epidemiologist, causal inference wasn't invented by Rubin in 1974 or by my friend Jamie Robbins in 1986. It's something we've always done, and it's always involved looking across all the evidence. But the set of methods that have been now labelled as causal inference, particularly revolve around potential outcomes approaches and counterfactuals, which are more or less the same thing. And they particularly use a randomized controlled trial model as the model for causal inference. And that's really useful sometimes. It's not a new idea. I did studies in the 1980s where I was using an RCT framework to try and think about how to design an epidemiological study well. We didn't give it a name. We were just trying to do good observational studies. But thinking about the corresponding RCT can be very useful. And there's some concepts which are not new, but it's thinking about what the RCT would look like helps you to think about what time zero would be like. Clearly define the risk period and the exposure, the estimand, and so on. So these are all helpful comments, helpful approaches, but they're really just embellishments of what we've always been doing. And so in the old days, when I'd analyze a data set, I'd define the populations and the exposure and the risk periods, and I'd try and identify potential confounders, and I'd try and adjust for confounders and avoid adjusting for mediators and colliders. And I'd run a normal regression. And the assumption behind that is always that if the model is correct, you're assuming there's no residual confounding, there's no other biases. Nowadays, the same thing has been put in different terminology. So we think about the target trial. Each participant has two potential outcomes, only one of which is observed. We think about exchangeability, consistency, positivity, and so on. And we use the outcomes in the treated and untreated groups to estimate the average treatment effect in the study population. And then we run exactly the same model that we used to run before. And for most of these methods, they don't change anything about the way I analyze a data set. They're useful for thinking through the concepts behind it. And particularly if you've sort of been trained in that RCT paradigm, it's very useful to think of those fundamental concepts. Concepts like time zero are useful, but they're not necessary. And most of the time, it doesn't change the way we actually analyze data. And for a long time, I had the point of view that all these concepts, it's good to think about fundamentals. It's good to have people thinking about them and working with them. Doesn't really change what I do, but it doesn't do any harm. But unfortunately, I think that's now no longer the case because of this whole idea of target trial emulation. And people have really taken it a step too far because they're now not only thinking about what their target trial would look like, but they're trying to make their epidemiologic study look exactly like the target trial. And to the extent that they end up throwing away a lot of data. So this is one example done by friends of mine. It's a very nice study comparing essentially the Moderna and Pfizer vaccines. And I believe the results. But the interesting thing about the study, it's based on the US veterans cohort, is that rather than just analyze the whole data set, adjusting for calendar date, age, sex, race, urbanicity, and geographic location, which you could do very simply, they actually matched on those things. And to do that, they threw away 43% of the data. And so they threw away almost half their data to make it look like a randomized trial. But of course, you'd get the same answer by analysing the whole data set and adjusting for those things. More or less, there'd be a bit of random variation or some variation due to effect modification. But you get the same answer with much narrower confidence intervals if you just analyse the whole data set and adjust for those same things. And it really brought home to me the way that this ideology of the RCT and the target trial emulation is doing real damage to epidemiology, because it's forcing us into a mindset which involves throwing away a lot of data. And a second problem, which relates to the analyses we've seen here, is that once you've done that, you can't assess confounding anymore because you've matched on those things. And you've removed confounding by the things you've matched on, assuming they're correctly classified. But in the old days, we would actually analyse the data set simply adjusting for age and sex, and then try adjusting for all these other things and see what direction does it move in, how strong does the confounding look like. And that helps us to assess residual confounding and how much might be there and what direction it would be in. Once you've matched for those things, you can't do that anymore. So you can't actually do the sort of sensitivity analyses that are an important part of epidemiology. So to come to this paper, which I think is a fantastic piece of work, it says that it's comparing traditional methods of analysis with causal inference. I would say it's doing something much simpler than that, because if you run a regular regression adjusting for confounders and you're convinced there's no residual confounding, then you're doing causal inference. There's no other reason we would do it. This doesn't compare traditional methods with causal inference methods. It compares traditional methods with entropy weighting and entropy balancing weights. And that's a very interesting comparison, and it's done very well. It's justified in terms of separating the design from the analysis stage. That sort of weighting or matching is actually not an inherent part of the causal inference approach, although some people are starting to use it in studies like this one. It's not inherent, and there's actually other aspects of the so-called causal inference approach which are not followed. And the most obvious one is that the real strong advocates of the causal inference approach, particularly at Harvard, really believe in this concept of time zero, and you should only include people who are followed from time zero. And we've had a lot of debate in different journals about what happens if you start with prevalent exposures. So you start with someone who's already been exposed for a long time and follow them forward. Now, the advocates of pure causal inference would actually throw those people out, and you would only follow people from time zero. Now, what's time zero for air pollution? It's the day you're born. We're all exposed to air, all of the date of conception. So if you've really followed a pure causal inference approach, you could only study air pollution in birth cohort studies, and you wouldn't have any data on the old people where the air pollution is doing the most damage. So I think the authors of this paper have quite correctly not followed the standard causal inference approach, because it doesn't work for this sort of problem. So when we're analysing a data set, we have essentially, as has been nicely summarised, we essentially have a choice of three methods. We can just analyse the whole data set the way we always used to, using some sort of maximum likelihood estimation. And there we're essentially standardising it because it uses maximum likelihood, but you get estimates that are very close to what you would get with direct standardisation based on the confounded distribution of the overall data set. So it's standardised to the study population. You can match, in which case, like the example I showed, you end up throwing away a whole lot of data. You're now estimating the causal effect in a subpopulation, or you can use some sort of weighting, including these entropy weights, which essentially give you the average treatment effect in some sort of undefined equipoise population. The advantages of each, maximum likelihood uses the whole data set, so it always, give and take a bit of random variation. The old-fashioned way, just analyse the whole data set, will always give you the smallest standard errors, just because you're using all of the data. For the matching, you're throwing away a lot of data, so you're inevitably going to have larger standard errors, even if you get the same point estimate. And for the weighting, it essentially has the same problems as matching, and that you're effectively throwing away some data. But the one advantage of these entropy weights is they do seem to give you the smallest standard errors. So they're almost as small as what you get if you just analyze the data set in the old-fashioned way, but they're still going to always be a little bit bigger. They're also always going to be a little bit bigger because any form of direct standardization is always unstable due to small numbers in particular strata. So it will always give you standard errors that are slightly bigger or sometimes much bigger than just analyzing the whole data set in the usual way. Disadvantages, the standard maximum likelihood estimation works fine unless you have to adjust for 30 or 40 confounders. And then propensity scores may be very useful just to reduce the number of things you have to adjust for. They have other problems, and they don't work well with imputation. It's often difficult to estimate. Sorry, the matching doesn't work well with imputation. It's often difficult to estimate the standard errors. And one problem of both of these approaches is, like I said, you can't actually assess residual confounding because you've sort of removed confounding to the extent you can by doing the matching or doing the weighting. And so you can't do what we used to do, which is to try not adjusting for the confounders and then adjusting for them and seeing what direction it moves them. So it actually reduces your ability to be able to assess the validity of your findings. So this study, I think what they've done is great. They have examined a lot of different models. I don't claim to have understood all of it, so I'm going to focus on the bits that particularly interest me. And I'm particularly going to focus on comparing the linear and the linear entropy results. So you would have seen here that for the linear model, essentially all of the different models they ran were unbiased, but the old-fashioned normal regression actually has a smaller standard error than you get with the entropy weights. But on the other hand, they show that if there's an interaction and you don't take account of that in the model, then the normal old-fashioned linear model seems to have more bias, but it still has a slightly smaller root mean square error. So what does this tell us? For me, it's not comparing causal inference, traditional methods with causal inference. Both of those analyses are trying to do causal inference. They're just doing it in different ways and using different labels to do the same thing. What it's actually doing is comparing traditional methods of analysis with entropy balancing weights. And they find that when the exposure effects are homogeneous and essentially the model is correct, then both sets of methods are unbiased. But the traditional methods have smaller root mean square error, which is exactly what you'd expect, because any sort of weighting or matching will always produce slightly greater standard errors, or sometimes much greater standard errors. They also find when the exposure effects are heterogeneous, the traditional methods are more biased, but they still have a slightly smaller root mean square error. So if the model's correctly specified, then all of the methods are unbiased. And one point to emphasize is that these different methods are actually giving you the average treatment effect in different populations. Running the normal regression is giving you the average treatment effect in the whole study population. If you're matching, you're getting it in a subgroup. If you're using entropy weights, you're getting in a ill-defined equipoise subgroup. So the findings are not directly comparable between the methods because they're looking at different subgroups. However, if there's no interaction, then the effect estimate is going to be the same in every subgroup. So you're going to get the same effect estimate in whichever model you run. They're unbiased. The traditional methods have smaller root mean square error because they effectively have a larger effective sample size, and they are also more efficient statistically than standardization or inverse probability weighting, which is essentially the same thing. Matching throws away a lot of useful data and effectively reduces the sample size. Entropy weights do the same thing to some extent, but they seem to be much more efficient, and they give you smaller standard errors, but they're always going to be a little bit bigger usually a bit bigger than what you would get just by running an old-fashioned analysis on the whole data set. And the different methods are comparable because they're adjusting for the same thing. And if there's no interaction, they're dealing with slightly different populations, but you're going to get the same result. You're just going to have different confidence intervals. If the model's incorrectly specified, in other words, if there's no interaction term when there should be one, then the traditional methods still have a smaller root mean square error. That's always going to be the case. However, in the simulations considered, the traditional methods are more biased than the entropy-weighted methods. And I'm still trying to understand why that's the case, and I'd be really interested in hearing people's explanations of that. But it's also worth making the point that if there's an interaction, then the results from these different methods are not comparable because they're being done in different populations. You know, it's either the whole population or it's a subgroup because you've matched, or it's an equipoise subgroup because you've used this weighting. So you wouldn't expect them to give the same results. Whether you will always get differences in this opinion, in this direction, with the traditional methods being more biased than the entropy-weighted ones, is something I think needs exploring. And you could well try different simulations to see if it depends on the assumptions of the simulation. So the entropy-weighted methods are estimating the average treatment effect in the equipoise population, and the traditional methods are estimating the average treatment effect in the full study population. So just to finish off, as an epidemiologist, I think it's a fascinating bit of work, really well presented, really well conducted. It's not something that's it's very interesting. It's not going to change the way I analyze a data set. I don't think it's comparing traditional methods with causal inference methods. I think it's just comparing traditional methods with entropy weighting, and that's an interesting comparison to do. And what this shows is if the model is correct, then the traditional methods are preferable. If the model is incorrect, then the two methods are not comparable, but there may be some situations in which the entropy weighted methods are superior. So thanks very much for the opportunity to comment on what's a really interesting piece of work. And I'm very pleased to propose a vote of thanks to the speaker, and I look forward to hearing the rest of the discussion. Thanks very much.
Thank you. I'd like to call on Dr. Ben Swallow, University of St Andrews, to second the vote of thanks.
Thank you very much. So yes, I'm a lecturer in statistics at St Andrews and Stats Department, and also a member of the Centre for Ecological Environmental Modelling. So again, I'd like to reiterate my thanks to the authors for a very interesting paper, and also the nice talk that we heard summarising that earlier. So it's always difficult with these talks because you never quite know what the other speakers are going to say or what the other proposer is going to say. So hopefully some of this will tie in nicely with what Neil has just said as well, but perhaps providing a slightly different perspective on this as well. So we can all agree that clearly the particulate matter impact on health is an important aspect that really needs consideration for all of the reasons that we've heard about already, and particularly for practitioners new to these sorts of methods of thinking, more from a causal inference perspective. It's often quite difficult to explain why we need to think more carefully about the design of the regression methods, perhaps over more traditional approaches. So we should definitely congratulate the authors on a nice manuscript that helps explain some of these methods using code that's readily available to practitioners who maybe don't have the statistical background, enabling to write these functions or these particular approaches themselves. However, I wanted to raise a couple of points that I thought perhaps needed to be discussed in more detail for these types of observational studies. As somebody who deals with a lot of observational data and thinking about some of these causal impacts, one of the problems we often come across is the idea of missing data. And that, to me, didn't seem to be discussed at all in the manuscript. We've done some work with the Scottish population using the EVE2 dataset, for example. So this is a very carefully monitored and structured dataset that was built up during the COVID pandemic. Scotland has a great system of data matching and data linkage. So in terms of the process, excuse me, of data collection, then it's really one that has a lot of potential. But even in that case, we had, for example, nearly 10% of missing data for the BMI for this population. And the idea, as Neil has already said, deleting data isn't a good idea. But thinking about how we might do imputation when we know, for example, missingness in a lot of these measures isn't missing at random, which is often an assumption required for imputation in causal inference, is potentially a problem. So I think it's really important that we specify what types of assumptions are made about missingness, how we go about imputing those or thinking about that, and approaches for doing it. And a lot of the assumptions is that causal inference type approaches assume data are missing at random. There's been further assumptions built into the three that were specified by the authors, namely this one from Rosenbaum and Mubin in 1984. And the idea is here that we can assume a covariate cannot be a confounder when it's missing, but it can be a confounder if it's present. And in a lot of cases, we have some measurements where we observe some of the covariate values for some parts of the population, but not for others. And the idea that that covariate can be a confounder for the people that we observe, but not for the others, seems relatively difficult to accept. So I think there's some further work needed doing here, and I'd be interested in the author's comments on that. At the end of the last year, we had a very interesting discussion meeting presented by Evans and Didelez on causal models, specifically marginal structural models. And they proposed this approach to be able to simulate and really focus on the causal mechanism of interest rather than worrying too much about how to simulate these complex models themselves. And they proposed an approach for continuous exposures, whereby they use a copula to propose the relationship on a marginal scale between the observations and the exposure, and that allows you to really build in these strong relationships. If you want to explore the structure without necessarily knowing, you can have these very, very flexible approaches, and then using CDF inversion gives you the actual observations. So given the flexibility of copulas, it would be interesting to hear the author's comments on how this might affect their approach to differing exposure response curves. As I say, it's a very recent work, so it's maybe not something that was discussed at the conception of this work, but perhaps some thoughts about how you might build in normal semi-parametric copulas to assist with this flexible exposure response curve estimation would be interesting. And finally, thoughts about model selection. So again, Neil made some interesting comments there, which I hadn't seen beforehand, but trying to think about how we go about selecting between what was referred to as more traditional approaches, when obviously these types of approaches are perhaps answering slightly different questions under different assumptions. Can we develop sensible practitioners? So as a practitioner, often model selection is a really important part of the inference procedure. There's always this kind of bias variance trade-off, but we have very strong practitioner recommendations for how we do this in a more standard regression framework. So how do we go about building this into, without doing these very in-depth, in-depth simulation studies that we can't really expect an average practitioner or epidemiologist to do every time they have a new data set? Can we make some suggestions about how they might incorporate this into a standard routine of comparing models, but also testing individual models? So in summary, I'd be interested in discussing or comments on missing data, the engagement with marginal structure models as a way of doing these sorts of causal inference that maybe generalizes to more standard causal or non-causal traditional methods, and finally, better methods for relative and absolute goodness of fit for causal inference. But on that, I'm also very happy to offer the second to the vote of thanks. Thank you.
Yeah, so thank you to all the presenters today for their excellent, insightful talks. And now actually it's tradition at this point, we've finished the vote of thanks that we give applause to the speaker and both discussants. So now we move on to the open discussion session. We encourage you online and here to comment or raise a question on the paper. It can be brief or up to 5 minutes long. If you're here at Imperial College, then in a moment you can raise your hand, and I will ask you to come up just for the recording for YouTube. Just give your name and affiliation. Online, you can use the raise hand feature to speak in the chat. And then if you like, your comments can be written up in the journal afterwards and submitted for publication along with the paper, providing a nice kind of archive of the whole meeting. But we start before the completely open session. We start with those who've given their names already. First, I want to call upon Professor Patrick Brown from the University of Toronto, who is online. So I will stop sharing, and Patrick, invite you to turn on your video. I'll mute myself, and you can share screen if you like as well.
Okay, I hope this is all here, except now I've lost my mouse. Okay, well, yes, thank you for the interesting talk, and I'll acknowledge Zhang Zhang and Sam Perot, who are also here, for contributing to this discussion. So first, we would like to congratulate the authors on their commendable work. In this paper, the authors investigate the comparison of various exposure response curves and estimation methods under different data generating mechanisms. The methods examined include regression-based approaches such as linear regression models, generalized additive models, and threshold models, along with their design-based counterparts derived from causal inference frameworks. The simulations show that in the presence of interactions between exposures and confounders, and when the exposures follow a linear relationship with the confounder, the design-based methods from the causal inference framework generally outperform their regression-based counterparts. An exception arises when the true exposure response curve exhibits sublinear behavior, and when the design-based method entropy GAM performs worse than the regression-based implementation, the standard GAM. And the authors conjecture that this exception could stem from an insufficient number of knots placed in the low exposure region. So on to our comments. There's two principal classes of spline smoothing methods. You can use regression splines or penalized likelihood. Regression splines are unpenalized, and users must manually balance an appropriate fit and overfitting by adjusting the number and placement of knots of basis functions. The penalized approach manages this trade-off through an estimated smoothing parameter which penalizes the coefficients on the basis functions. Typically, a quadratic penalty is used, and a specific penalty matrix on the coefficients is equivalent to applying the integrated squared second derivative penalty on the underlying function, as Green and Silverman showed. As the number of basis functions increases, the behavior of this penalized curve converges to a Gaussian process known as the integrated Wiener process, exhibiting behavior described in Zhang et al. 2024. The limit gives the penalized models consistency across different data sets and reduces the sensitivity to the number of knots. So I will move down to keep the figure up here while I read. You'd figure I would have learned how to use Zoom by this point. So in figure X here, we repeat the simulations from figure 2 in the manuscript, fitting 3 different spline smoothing methods. The first is what's implemented in the GitHub code, which uses the GAM package with 4 basis functions and a second derivative penalty. The second method, which is in green, is the method implied when table 1 lists 4 degrees of freedom in spline smoothing. It's sort of the way we read that was implying an unpenalized regression spline. And then the third method is 100 basis functions, which are penalized, and we intend this as an accurate approximation of the continuous Gaussian process. And the smoothing parameters are estimated in maximum likelihood. So one conclusion from this figure is that, contrary to the author's conjecture, the poor performance of the entropy-based GAMs in this scenario are not caused by the placement of knots. The unpenalized regression splines, which are the green symbols, are in most cases a modest improvement on the 2 penalized methods, while the 100 basis functions in blue are comparable and slightly better than the 4 basis function penalized models. The results suggest that 4 basis functions is sufficient in this setting, and penalizing is unnecessary. However, the true exposure response curve here was quite smooth. The result might not hold for problems where the underlying ERC is rougher. And in Peroto 2024, we found that the prediction intervals and coverage probabilities can be very highly sensitive to the particulars of your smoothing method, even when the point predictions themselves are quite insensitive. So the question is, are the authors advocating for regression splines with a modest number of knots as the preferred method for ERC estimation and air pollution studies, perhaps relative to other types of model assumptions like independent observations and so on? Is limiting the curvature of the ERC just a minor concern, or are there circumstances where a more flexible model with a principal choice of smoothing parameter is warranted? Thank you.
Thank you. Thank you. Right, so we now move to contributions from the floor, online, or here in person. If you have any, then please do raise your hand. As you see, actually, I have by mistake. So please do raise your hand online or here. Feel free to come up. Andre, please do. If I could ask you, give your name and affiliation when you come up, and just sort of stand in the vicinity of the microphone and video. Thank you.
Thank you.
So just a thank you.
I'm Andrei Srakar. In the discussion paper committee, I represent the emerging applications section. So I congratulate naturally on the excellent paper. My comments surely relate to the basic causal inference framework that you have. I, in principle, agree with the first discussant that here probably the question is maybe not so much about comparing causal inference methods with regression. So what I slightly didn't understand, at least from the presentation, is the actual causal problem and the reasons basically also why the exact causal estimates and everything was used. So you're naturally using observational data. There has been recent study of imbalance and with the imbalance and Iching Chu in 2024 when they explore recipes for correcting for the problems of observational data. For example, they recommend double robust estimators and so on. So what I slightly missed, at least in the presentation, is more concise definition of the causal framework, and also questions naturally were raised. You mentioned the 3 or 4 general assumptions that we all know about the causal inference, like unconfoundedness, overlap, Sutva, and so on. What would happen, for example, in this framework, if they would be violated, which is a common thing? Say, if you violate Sutva, you have treatment defense with network interference and so on. So how to maybe more concisely define here the actual causal framework, the actual reasons why to use specific causal estimators, which would be the best. So this definition of the actual maybe exact causal framework naturally for observational data. There could be extensions, mentioned Pearl and so on, but already this, at least to me, was interesting to remind. Thank you.
Anyone else in person? Any comments or thoughts? Do we have any more online? Yeah, Dan, please come up. No, you have to come up. I'm sorry. Even if it's a short, the microphone won't pick you up.
It's just more like related to the motivation of the paper, but it's not specifically to something from the paper. Well, hi, I'm Daniel. I feel weird when I should not say that. Sorry. Well, that edited. that. Yeah. Now, first of all, congratulations on the paper. Really cool. It's very cool also that you studied both the small sample and the large sample problem. Most of these methods applied back in the early 1980s. We really didn't have these data sets with hundreds of thousands of rows, right? It was quite interesting that the change point methods failed to converge with so many data points. It might be that they're just too biased, but that's another thing. My question is, going back to what was said about what is the actual causal question in the study? Because I was trying to think of this in a prediction-based setting. In prediction-wise, you would be interested in understanding how PM helps you predict a decrease or increase in mortality rate, right? But you want that to be a direct effect of the PM measurement, which is, of course, correlated with the confounders. But in some way, how do you address this in a predictive form of thinking? Or if you only had access to the PM variable, how would the results differ rather than using all the confounders, adjusting for them, just not including them in the model, if that makes sense? Did you look at the residuals and the mean squared error, not of the estimation of the ERC curve, but of the simulated Y's, which would be what we observe in real life? Because I would be interested to see whether or not that the regression method might be very good at estimating that mean response, but the heavy tail, both in the exposure and the residuals with, I think it's a variance of 100, right? Does that affect predictive performance in some way? Whereas the confounders with the smaller bias could have better predictive performance, even though they don't estimate the mean as well. But that's just curiosity. Thank you.
Great. Thank you, Daniel. Cool. There's no more come online anymore in person. All right. That's fine. So as we've reached the end then of this discussion meeting, I'd like to call on the author, Michael, to reply if he wishes. It's entirely optional, but up to 10 minutes. You can, of course, give a more considered reply later in the journal. But yeah, the floor is yours. I can even turn the picture off not to distract everyone. It's all yours.
Well, first off, I want to say thank you for the questions. It's pretty cool as a, I feel like when I imagined what would be a cool way to present a paper is actually people really engaging with it out the bat, and often we don't get to hear this back and forth. So it's really a privilege to be able to do it in person. I want to thank the discussants. I think those are really great points, and also didn't shy away from being hard hitting, which I also love. So I would love to give some of my takes. I'll start with some of Neil's comments, which I think are really helpful and useful to think about, because I think in statistics or in all of science, we can often get infatuated with labels on like what we put on things, right? So causal inference has been developed as a framework. And I think it is true that sometimes we can really attach the idea of causal and causal framework as if causal inference methods, which are just a branch, I would say, epidemiology, statistics, and computer science. But actually, in econ, if you ask anyone there, they'd have different opinions on it. But right, there's no sort of, they don't own the idea of causality. And I would agree too that epi has always been framed. Anything when we fit in statistics has often been framed as a causal question. I think that's how we make decisions, and that's how we like to think, right? We're measuring things not because we care about associations, but we're trying to answer causal questions. So one thing that I would just say is why I think they're different, because I do think they are actually different, is that when you're fitting a kind of like, when I call traditional methods, and I'm calling them regression methods, that is just to say that they are not framed in this causal inference framework. And I think the advantage of causal inference framework, though it can get lost in the language, I think it's important to be mindful of, is that you are just a little bit more explicit about what type of confounding adjustment you're doing. So when you're fitting a linear model, right, versus fitting an entry-based method, right, the linear model is actually, you can think of it, there's actually a really good paper on this, you can think of it as you're actually implying a propensity score model in itself, right? When you fit a model where you adjust for the covariates linearly, you're actually assuming some sort of relationship. You're assuming, right, and what I've shown in this paper is that if the confounding structure is linear, then it does okay. But I think it's just to say that causal inference methods are more explicit, able to adjust for maybe different forms of confounding than if there's kind of a more standard linear case. I want to also make a comment. I think there's a really interesting point about how this changes, right? How we might think of, right? If you do a matching structure, right? And I think you said, right, often you can do an analysis in epidemiological study where you include more covariates in the model and you can see how the effect estimate changes, and that it's harder to do in a matching framework. I would point that I think the most natural comparison is you can actually adjust what kind of covariates you're matching on. So you could just add more or less variables and see how that affects the estimate. And I think so I think that's kind of the equivalent sensitivity analysis. But I think causal inference methods can go one step further in the sense that, right, when I talk about this e-value analysis, it's trying to get at how strong would an unmeasured confounder have to be to bias this relationship. And so I think that's another sensitivity analysis that is important. And I think this relates to one of the comments that someone said, which I think is really true, which if I have more time, I would love to do, which is what happens when these kind of assumptions are violated, right? Because I think that is a natural next step. Just given the fact that I had already undergone a lot of different simulations for this study, it didn't I didn't include this in this particular simulation study, but I think it would be really interesting to say, okay, what happens, for example, when we have some violations of positivity that are really apparent, and we can really document a certain way, or unmeasured confounding, or SUTFA. And so I think that is a very valid point, and I would love actually to see that if, in the field. Let's see. I also just want to make one little point about one of the discussions that I think Neil was presenting about the ATE, which is the case that I think you're very valid points about, right? When you're doing weighting, you have to be really careful of what are you actually estimating, right? Who are you estimating, for example, when you're thinking about the ATE, when you're doing inverse propensity score weighting, when you're doing entropy weighting, it's probably maybe a different population than if you're just doing other methods. But I want to be clear here that we're actually in a continuous exposure setting. So it's actually slightly different in terms of when I'm evaluating the exposure response curve, right, I have infinitely many values I'm imputing. So in this methodology, to my knowledge, I think they should be comparable because of the way that I'm going about this method. But though, any comments on that, I think are really valid. And I think it really highlights that it's really important to be really specific, which when I think about what causal inference is doing is being just slightly more specific about what it is that we're measuring. But again, I think it's a really valid point that we can sometimes get lost in the label and thinking that that is, inherently better than other times. Okay. I was really interested by the second discussant's idea about missing data. I think that's another thing that could be really interestingly incorporated, right? What kind of censoring is happening? I was actually not as familiar with the method of copulas for kind of using that in to inform like a simulation study, but that has got me really interested. So I'll definitely be looking at that. So thank you for that comment. And then, yeah, as Adam was saying, I'll definitely love to, give me a lot to think about. I'd love to respond more. But I think I have a couple of other small comments. So also, thank you, Patrick Brown, for doing that analysis on the GAM and including different models. I think it's really an awesome thing to have, is someone actually going into your paper and looking at one of your conjectures and saying, actually, it's probably more complicated than what you said. And I think there was a question on right, is there value in adding more flexible models? So, right, when I fit a spline with a degrees of freedom of 4, that was done because it's kind of, right, that's a smoothness assumption that I'm making that I felt was appropriate in this PM application, though, of course, there's reason to kind of also choose methods that maybe, there are methods that can penalize and kind of choose an appropriate degree of freedom based on things like root mean squared error. So I think that that's a really important thing to think about, and I'll definitely comment on more. And one comment I think I got about the predictive performance by Daniel, I think that is really interesting. So it turns out, right, and this is actually more a general comment, and I think this is a fair point, which is saying, right, you're not, right, when I'm saying causal inference versus traditional, it's like, is it just entry balancing versus traditional? I want to note too that I did include a causal GPS, which is an entirely different way of thinking about it. So entropy weighting is kind of a stand-in for a causal method that I think is important in this context, though there are many others. But one of those is formed on like G-estimation, right? The idea is you're actually imputing the outcome. So in that case, right, you're actually getting at identifying the exposure response curve, or in a binary setting, the ATE, using basically a model that you're trying to train on the outcome data. So it's kind of framed this predictive way. And in doubly robust methods, you actually combine both kind of an outcome model and a kind of propensity score model. And so in that setting, it makes sense that you want to see how well you are doing in terms of imputing the actual observed outcome. And in my setting, it can be really challenging because we have so much model infrastructure from computer science and other fields on how we can try to think about how well are we modeling the outcome. It's a lot harder, and something I struggled a lot with is how well are we doing at fitting this curve, which isn't actually the main kind of like, what I would say the main end product of a model, right? You still have to kind of impute this curve. So I think it's a really interesting question, and one that I think is worth looking at, especially given that there's, I think, a lot more infrastructure being built for that kind of question versus one where you're trying to look at an exposure response curve. There was one last comment. I've written down a couple of these by Andre on the causal framework, and actually I'm not sure I'm going to get this question right, and I'd be happy to comment more on. So in this case, right, there's a lot of different causal estimands that could be useful and important. I chose to select the exposure response function just because I think I see that in the space of air pollution epidemiology, that's one that's often used. I think you're right, and I would love to kind of go back and just be more clear about exactly why I chose that or how I'm estimating it. I think you said something about double robustness, and I just want to give a little comment about double robustness because I think that's another similar to Neil's comment of causal inference, where I think we get a little bit lost, because in this sense, when we say doubly robust, often we're meaning that we're fitting two nuisance functions really explicitly. But doubly robust is complex because it actually turns out that most models, you can formulate double robustness as long as certain conditions are met, right? Even if you fit a linear model, there is actually an implied sort of distribution of the exposure that if that is correct or the outcome model is correct, you're going to get an unbiased estimator. So I think we can also, that's one of those words that, this is kind of me going on my soapbox a little bit, but I think it's really interesting because double robustness is another word that I think we have to get really specific about in the same way maybe when we say causal inference, because I think to someone who's not steeped in the field, it might convey something slightly different than when you get really specific about it, what it actually means. So I'll just add that comment and I'd be happy to respond more. But I just want to thank everyone again. This is a really cool experience to be able to see people who have really deeply engaged with my work, using code. And so, yeah, thank you.
Thank you, Michael. So as Judith has said in the chat, we welcome contributions to the discussion at any time up until the 10th of January in writing. These should be up to 400 words, so please do keep to that. We do come back asking you to trim it if you are tempted to go over, but that is not including references, tables, and figures. But don't overload the figure caption, that's cheating. For full details and how to submit to Scholar One, email journal@rss.org.uk. Judith has put that in the chat for those online. And similarly, that's the same email you can use to get an invitation to future discussion meetings, get a direct invite. So please do email that, and you can be added to the discussant mailing list to contribute to future meetings. And full details of all meetings are available on the RSS website. We don't have a date yet for the next one, but there are ones coming in 2025. So this is the last one, obviously, of 2024. Finally, I just want to personally thank Department of Maths at Imperial College London for agreeing to host this meeting and providing a venue. I'm very grateful. And we also have some tea and coffee upstairs on level 5 in the common room. So anyone who's not from Imperial and doesn't know, just sort of follow us as we leave up to the 5th floor of the same building. Those online, perhaps make yourself a tea and coffee in absentia. Sorry you can't join us, but hopefully you can join us next time. Thank you very much, everyone.